Assalamu alaikum warahmatullah. In this video, I'm going to show you how you can determine the equation of the induced voltage in a synchronous generator for unity power factor, leading and lagging power factor. To start, let's draw the equivalent circuit of the alternator. So to start, let's represent the induced voltage by ET here. Okay, the reactance of the synchronous generator and the resistor of the armature RA, and the voltage at the terminal of the generator. It is a single phase equivalent circuit. Okay, so VT will be induced in between those two terminals. Okay, and the current will be represented by IA. Okay, we can add to this circuit, equivalent circuit, you can add the winding, the field winding, to excite our generator. So this winding will be excited by DC voltage, and current IF will be circulating in this field winding. It will induce the field flux. This flux will induce ET in the other side. So for power unity power factor case, so power factor case, okay, let's draw the triangle. So we have VT. If you can use KVL in this loop here, VT plus RA IA and plus X, the voltage drop across the reactance, JXSIA. Resultant voltage ET will be represented here. Of course, and we have the current is in phase. That's the power factor, unity power factor. So this is IA here. So the equation of this induced voltage will be ET equals VT plus RA IA and plus J XS IA. Now, to determine this ET, we can square this, which is VT plus RA IA. We take the real part of this equation, squared it, and plus XS IA square. Okay, so finally we can find ET of this is per phase. This phase voltage will be equal. The VT also should be per phase. Okay, so this will be square root of the real parts. Okay, we're going to rewrite the equation. Okay, plus XS IA squared. So that's the induced voltage for unity power factor. Okay, now, okay, let's do the other one for lagging power factor. Let's change the color for this case. So for lagging power factor, let's represent the triangle. Now take, let's say this is VT. The current is lagging by theta, for example. So this is IA, and R will be this way, the drop across R. So RA IA Okay, the G, make it a little bit longer just for to have a clear graph. So this is a JXSIA. The resulting voltage will be ET. Okay, so now to find this the ET, and keep in mind this is per phase all the time. We're going to project this current like that. Continue the line. So imagine this line is straight like this. We project that. By the end, we need to make like a right angle, okay, right triangle, sorry, here, in order to find ET. So according to this triangle, okay, make it from the middle here, like that. Okay, so let's take, okay, the right triangle. So we have ET squared will be equal this segment here, okay, from here to here, and that is VT cosine theta plus this portion here, which is equal to RAIA. So this vector equals this vector here. So plus RAIA and square plus the other section here. It has two portions. The first one, which is equal to this, so this vector here, or this segment, equals that segment, which is VT sine theta. So VT sine theta plus this part here, which is XSIA and squared. Okay, so general equation, just write it here. ET will be equal square root of VT cosine theta plus RAIA squared and plus VT sine theta plus XSIA squared. So that's the per phase. And phase here. Okay, so this is the equation for lagging power factor. For any lagging power factor here, okay, we can determine the equation using this equation here. The equation of ET using that equation. Okay, now for a leading power factor, okay, let's represent our graph like this. This is VT. Okay, the current is leading. So for example, this is IA and that's the angle. Theta. So the resistor will do the same, go the same way. Let's make it a little bit bigger here just to have a clear graph. So this is RAIA. Okay. This will represent the drop across XS. And the resultant voltage ET will be this way. So now do same thing. We'll project this vector here, the current vector. Okay, let's make right angle again here. And also right angle in this section here. So ET squared will be equal this part. This part consists of Vt cosine theta, so this section. So Vt cosine theta plus this section here, which is Ra Ia squared. That's this segment here, plus this part only, which represents all these segments, which is equal to this one, should be in parallel and they are equal. So this part here represents Vt sine theta, this section, and we take off from that section this part here. We remove xs Ia squared. Okay, so the objective is to find this part, okay, and this part here, okay, with the right angle, that is et squared equals this part squared plus this part squared. So this is you can see it, it's cosine theta, Vt cosine theta, this section, plus Ra Ia, which is this segment, equals to this segment here. Okay, now this segment here will be equal to all this segment, and if we need that portion here, we can take off the can take off from a Vt sine theta, we can take off this xsia, and that is represented here. So the final equation per phase be equal to square root of, this is for leading power factor, Vt cosine theta plus Ra Ia squared, and plus the other section Vt sine theta minus xs Ia squared. So this is all per phase. So that is for how we can find the equation for the induced voltage of a synchronous generator. Thank you.